Welcome to Modern Machining Technology, course code BNM 30103. This study into high-speed material removal is based on the curriculum structured by Dr. Keiru Kamarudin. In classical manufacturing, there is a strict thermodynamic limit, as you increase the rotational speed of the spindle and ruins the workpiece. High-speed machining functions by bypassing this limit. Once the spindle crosses a specific extreme velocity threshold, the mechanics of heat transfer invert, creating a cooling effect at the cutting edge. This process pairs extreme spindle speeds with rapid feed rates and very light depths of cut. This approach achieves three distinct objectives. It increases overall surface quality, decreases production costs, and regulates the temperature at the edge of the tool. Managing that thermal load is the critical physical mechanism that allows for continuous high-speed material removal without pauses for dissipation. This interaction between speed and thermal transfer establishes the physical foundation for the streamlined production models we will analyze next. To see how that physics translates into industrial value, we have to look at the manufacturing pipeline from raw block to finished part. This is a sequential process map showing the traditional method. We begin with a soft, non-hardened blank. The material must go through roughing and semi-finishing stages to create the basic geometric shape of the component. At this point, the part has to be removed from the machine and sent out for heat treatment hardening. This introduces a major logistical bottleneck, stopping production while the metal is treated. Once hardened, the metal is too tough for standard cutters. Clearing out tight internal corners traditionally requires electrical discharge machining, or EDM, followed by manual hand polishing. Now look at the revised flowchart using high-speed machining. The thermal dynamics we established earlier allow the spindle to cut fully hardened steel directly. We take the hardened blank and immediately perform finish machining, replacing the slow EDM process. These large X marks show the elimination of the EDM and manual finishing blocks. Two distinct, time-consuming stages of production are removed. This condensed timeline is vital in aerospace applications, where complex, thin-walled frameworks are carved out of solid aluminum blocks. The engineering value here is time. By bypassing entire secondary manufacturing stages, an operation can compress weeks of production into days. To understand why the tool survives direct contact with hardened blanks, we have to look at the math behind the thermal bypass. In the 1920s, Dr. Carl Salmon modeled the relationship between spindle velocity and interface heat. He found that for any specific material, the temperature peaks at a certain critical speed. Once the cutter pushes past that peak into the high-speed zone, the thermal energy shifts away from the tool. Instead, the heat is forced into the sheared metal chips and immediately ejected from the cutting area. The critical velocity required to reach this cooling zone is relative to the material being cut. It depends on the molecular structure of the workpiece. This chart shows how those parameters shift. For heavy nickel-base alloys, the high-speed transition zone occurs at a relatively low spindle velocity. Aluminum requires drastically higher raw rotational speeds to trigger the same high-speed cooling effect. However, aluminum's operational bandwidth is incredibly wide, allowing for extreme velocities exceeding thousands of meters per minute. This table illustrates that the physical composition of the cutting tool also dictates the absolute speed limit within these material zones. In a mild steel workpiece, a cemented carbide tool allows turning speeds between 90 and 135 meters per minute, while high-speed steel is limited to significantly lower velocities. Reaching the thermal bypass requires exact calibration of speed, workpiece material, and tool composition. Pushing spindle velocities into the tens of thousands of RPMs places extreme mechanical stress on a milling machine. At these velocities, a microscopic imbalance acts as a violent force multiplier. The spindle develops a lateral wobble, tearing the mechanical assembly apart in seconds. To prevent this destruction, engineers must strictly control 7 interconnected mechanical parameters. This diagram outlines the 7 pillars of the high-speed system core. The first pillar is the rigidity of the tool and workpiece. Standard clamping is insufficient against the extreme lateral forces generated at high speeds. Second is tool balancing. At high RPMs, even microscopic weight asymmetries create catastrophic mass variations. Third is harmonics testing. Programmers must avoid the natural resonant frequencies that can tear machine joints apart. This physical stability must be matched with active management of the cut itself. This brings us to pillars 4 and 5, controlled tool load and chip thinning. Manipulating the feed rate creates chips that rapidly absorb and carry away heat, preventing it from saturating the tool or the part. The sixth pillar is cutter selection, requiring specialized carbides or diamond coatings designed for extreme heat resistance. Finally, material understanding. The entire system must be tuned to the specific atomic behavior of the blank. Without rigorous adherence to all 7 pillars, increasing spindle speed will simply result in the rapid destruction of the manufacturing equipment. We can prove the productivity of these systems using the mathematical model for high-speed turning. Engineers rely on these 2 formulas to benchmark efficiency, cutting time, and the material removal rate. The material removal rate requires 3 inputs: cutting speed, feed per revolution, and depth of cut. Let's apply this to the aluminum cylindrical workpiece in this schematic. We set velocity to 1200 meters per minute, the feed to 0.3 millimeters per revolution, and depth of cut to 0.5 millimeters. These precise calculations allow production managers to mathematically guarantee higher removal rates before a machine is ever turned on. High-speed machining functions as an integrated ecosystem of rotational velocity, rigid tooling, and material thermodynamics. Your academic task is to independently outline and debate the core pillar concepts required to maximize removal rates in this system. Modern manufacturing output is optimized by exploiting these physical boundaries through calculated engineering.